So this one is January 2020, Unit 4. We'll discuss MCQs. So in the first question, a neutron can decay to produce a proton. Which of the following equation correctly shows a neutron decay? As we know, neutron, it's a positive and a negative beta decay. When a neutron decay, what it gives? A neutron gives proton, electron, and anti-electron neutrino. Why there is an anti-electron neutrino? To conserve the lepton number. That's why there is anti-electron neutrino. And when a proton decay, it gives out neutron, it gives out positron, positive electron, and electron neutrino. That's also released. So it should be neutron and neutron decay into proton, electron, and anti-electron neutrino. That's why it matches with option C. This is actually a negative beta decay. If it was a positive beta decay, then the proton will break down. At a distance d from a point charge, so there's a point charge at a distance d, and the charge has a magnitude q, and the potential is v. Which of the following is the potential at a distance 4d? So there's another like 4 times d, the distance. What will the potential at a point which is 4 times d? And a point charge is having a magnitude of 2q. The formula for the potential for a point charge V is equals to kq over r. If it was electric field strength, it is kq over r square. So V is equals to kq over r. That's a formula for potential. So in the question, the charge is double. If a charge is double, what will happen to potential? Potential will also be double because it's directly proportional. And it is inversely proportional to R. So if R is increased by 4, what will happen to V? It will decrease by 4. So because of changing the charge, it will be multiplied by 2, and because of changing the distance, it will be divided by 4. So what is the overall change in the potential? It will be V by 2. Is it clear? In question 3, a ball of a mass m traveling at a velocity v strikes a wall at a right angle. So the ball strikes the wall at a right angle and it bounces off in opposite direction. So it moves in opposite direction, so it will be minus v. What is the impulse on the wall? Impulse is refers to the change in a momentum, and change in momentum is calculated by final minus initial. And the forward direction we consider as positive. If a forward direction, like as they mention here, with the ball of a mass m traveling with a velocity v, and it bounce off of the wall in opposite direction as the same. Which of the following is the impulse on the wall? So change in momentum, the formula which we use to calculate the change in momentum or impulse. If we calculate the impulse of the ball, so impulse of the ball will be what? It will be mv because it's a final minus initial. Mass is m. So for ball, it will be minus mv because the velocity and this my negative sign and mv. Final minus initial, so the total momentum will be minus 2 mv. That is for the ball. But in the question, because when two objects collide, they have same impulse but in opposite direction. So if the impulse of the ball is minus 2 mv, what will the impulse of the ball or on the ball? The impulse on the wall will be plus 2 mv because whenever two objects collide, they have the same magnitude of the impulse but in opposite direction. So the impulse on the wall or impulse of the ball, it will be 2 mv, but impulse of the ball or change in momentum of the ball is minus 2 mv. That's why option B will be the right answer for this. Is it clear? The next we have is the diagram shows an equipotential surface. Equipotential surface means that we have the same work done. Like when we move from one potential surface to another, we do same work done. Like if 10 joules of work is done here, same 10 joule will be work done here. But because the distance is more, so spacing will distance is more, it means the force is less because the work done is a product of force and distance. So for a weaker force, the spacing between the equipotential surface will be more. Now, which of the following diagrams shows a possible combination of electric field lines and the polarity of the charge? First thing, when we talk about the potential, the positive charges are considered a high potential. Like example, if I have electrode is there, I have two electrodes, so the positive one is considered as high potential and negative one is low potential. So the value is changing from high potential to low potential. So what this give an indication? This give an indication that it must be a positive charge. Otherwise, if it was a negative charge, then how the variation should occur? Like first will be 2, then it will be 4, and then it will be 6. It should be like this. But here it is 4. So higher potential is always positive. So that's why it must be a positive charge. And what is the direction of the positive charge? The direction of the positive charge is all like electric field lines are always pointing out. So A will be the right answer for this. Next is the diagram shows the potential applied across the two conducting parallel plates. So as you can see, this is positive and this is like lower potential. So this is a positive electrode and this one is a negative electrode. The point X is midway between. Which of the following electric field strength, even it is midway, even it is 1/4 of the way, 1/3/4 of the way, electric field is constant between the two electrodes. So V is equals to ED, where V is the total potential difference 10, E is the strength of electric field, and D is the distance, which is 20 centimeter or 0.2. So it will be 10 divided by 0.2. So it will be 50 volts per meter. That is, so 50 volts per meter will be the right answer. But then what about the direction of the electric field? As we know, like the positive one is like the higher potential is a positive and electric field lines are always pointing from positive to negative. So the direction is a downward and it is pointing from it is the magnitude is 50. So volts per meter. Is it clear? This one? Okay. Next, we have a gamma photon of energy 18 mega electron volt produce a particle and antiparticle. Which of the following will give the maximum possible mass of the particle in kg? So first, this photon is producing a particle and antiparticle. So photon is there that is producing a particle and antiparticle. Okay. Now then what we will, how we can work out that this total 18 mega electron volt will convert into half will be transferred to produce an antiparticle and half will be for the particle. So basically 9 mega electron volt will be the energy for creating a single particle. This we need the mass, so E is equals to mc square. So if I need the mass, energy divided by speed of a light, that will give us the mass. But energy should be in joule. This energy is in mega electron volt. First, I'll convert into electron volt. So mega means 10 power 6. So this will be in electron volt. And if if two particles are, will the energy, yes, if the two particles, because if particle and antiparticle are produced, they have the same mass. So that's why the energy will divide evenly. But if the particle is produced, like if two different particles are produced different masses, then the energy will not divide evenly. It will divide according to the ratio of their masses. But because here it's a particle and antiparticle, that's why the energy will divide evenly. So we have electron volt, we convert into, so 9.9 into 10 to the power 6 multiplied by 1.6 into 10 to the power minus 19, means this is converted into joules. And then divided by speed of a light, so which is 3 into 10 to the power 8 and then square. So 9 exponent 6 times 1.6 exponent minus 19 divided by 3 exponent 8 square. So it matches with option D. So D will be the right answer for this. In question 7, a current carrying wire is placed between the two magnetic poles. The magnetic flux density between the pole is 0.07. So the direction is out from north and into south. Now, to know the direction of the force on a current carrying conductor, we use a Fleming's left-hand rule. According to Fleming's left-hand rule, your index finger or first finger will point towards south, the magnetic field south. Your second finger represents the direction of the current, which is, in this case, the current is going in this way, and your first finger will point. So if your first finger is pointing down and your second finger is pointing, use the left hand. So where the thumb is pointing, thumb is representing the direction of the force. So when you work out the direction of the force, it looks like it's pointing out towards you, out of the page. Yeah, that's right. So means option with out of the page is right. Okay. Because when you apply the rule, you will find it is pointing towards you or out of the page. Then how to know the force? The formula for the force on the wire placed in a magnetic field is F is equals to BIL sine theta, because it is perpendicular in terms of the direction of the current, like the current, and this is 90 degree. This angle is not, I'm not talking about this angle, I'm talking about like if the wire is carrying a current and there's a magnetic field like this, when you apply the rule, you will find it is a 90 degree between them. So this sine 90 is 1, so it will be B, the strength of magnetic field. L is the length of a wire which is placed in a magnetic field. But not according to the diagram. Yeah, so according, you will always take a perpendicular component. Like that is, I'm saying. So you will take a perpendicular component of this. How to take a perpendicular component? Like, say, this is a wire for you. Here is a magnet. Okay. Now this is 6.5. This is 6.5 is there. So we need the perpendicular component. So this is a north to south, that's a magnetic field. So we need this component. And how long is this component? Like what is the length of this component? It is given 5 centimeter. 5 centimeters. So this component, like this length, this portion of a wire is 5 centimeter or 0.05 meter. So C will be the right answer for this. Is it clear? Next is point charge Q and negative Q are placed at X and Y. Another charge is placed at Z, the resultant force is 0. So if there is another charge placed and the resultant force is 0, which of the following could be the charge placed at Z? So if this is, and we are placing a positive charge, like charges, what they will do, the like charges, they will repel. So, and unlike charges attract. What is the direction of the force on the Q? The direction of the force on the Q is to be attracted. Okay. What about the direction of the force that is also attracted? Because what we want, another charge is placed at Z and the resultant force on the charge at x is 0. So the resultant force, we want the resultant force to be 0. Like if we compare the value of the charge here, value of the force, let's say this was force F, this is also force F, okay? Now we want to place another charge, unknown charge here, so that because it's a positive charge, so that it cause a force in opposite direction and the resultant will be 0. So if this distance between them is, let's say, between x and y is r, what is the distance between x and z? The x and z is 2r. So we want the same force. We have the formula that the force between the two charges is given by a formula Q1, Q2 over r square. We want F to be same. According to a question, one of the charge is Q that is given, another charge we will work out, but the distance is being double. If distance is being double, so if a distance is double, like example, if it is 2r whole square, so when we further simplify, it will be K Q over 4r square. I want the result to be same. I want the result to be KQ over R square. So how much is the next charge? It should be 4Q. Why it will be 4Q? 4 will cancel with 4. And again, what we'll get F is equals to K Q1 Q2 over R square. Because we don't want we want the same force but in opposite direction to cancel out that the resultant force is 0 on this. So if we want the same charge, but another charge is placed at this point, so what should be the magnitude of this charge? The magnitude of this charge will be 4Q. Because the distance is double, if distance is double, the force is decreased by 4. So we want the force to again increase by 4 so that it will remain unchanged. That's why it should be 4 times Q. Is it clear, this question? Any doubt in this? And if we want a resultant on at y0, okay, yeah, good question. If you want a resultant on y to be 0, look, the force F is here attracted. And if we want to place another charge, if this is distance r, this is also distance r. Because the two charges are pulling at the same distance. So if this charge is q, this should also be q. In that case, if I want a resultant on y to be 0, then this should be q. But I want a resultant on x to be 0 because the distance is being doubled, so that this should be 4q. Is it clear? So if we want a resultant on y to be 0, this should also be q, so that they cancel out the effect of each other. The diagram shows a momenta of particle Q and P and Q of two bodies after about to collide. When the body collide, they merge and single body. Which of the following shows a resultant? According to conservation of momentum, total momentum before must be equals to total momentum after. So we just have to add any one of them. We can draw first. You can draw Q first, then P, or you can draw P first, then Q. So we join the first vector, then the second vector and it should be in scale. Like example, in exam, you'll measure this length and draw accordingly. Don't draw just a random length. It should be according to the scale. Like if this is 4 centimeter and this is, let's say, 3 centimeters, so we'll draw accordingly. And then from tail of the first to the head of the last, when we join, tail of the first to the head of the last, that will be the resultant. Or you can draw Q first. You can draw Q first and then you will draw P. Again, from the tail of the first to the head of the last, that will be the resultant. This will be the resultant. So we want a resultant, only option in which the resultant is drawn correctly is C. As you can see the direction approximately. So C will be the right answer. Is it clear? Question 9. The next is in an electron deflection tube, electrons are released by passing electric current through a filament, which are what we call, when we pass the current through a filament, it produces heat energy and release the electron. We call thermionic emission. Photoelectric effect is when the light in the form of a particle or a photon falls on the metal and electron is released. We call photoelectric effect. Electron diffraction is when electron when electron is passing through a crystal, it's act like a wave, that is called electron. And ionization means when an atom is there, we remove electron from an atom, we call ionization. But in a thermionic emission, we pass the current, current produces heat. Heat energy causes this emission of the electron. So we call that as thermionic emission. The term thermionic means like a heat emission. So this was January 2020 paper 4.